Loss functions and optimizers. Let's get the big guns out. So here, loss functions and optimizers are essential components of neural network training, responsible for measuring the model's performance and updating its parameters to minimize the loss. Let's explore these concepts in depth. The loss function quantify the discrepancy between the predicted outputs of the model and the actual labels or targets. They are used to evaluate the performance of the model during training and guide the optimization process. The common loss function looks something like this. So let's go over the mean squared error first, MSE. Measures the average squared difference between the predicted and actual values. Suitable for regression tasks, mathematically it is represented as MSE equal to 1 raised to n summation of I is equal to 1 to n, and you pass and inside that you give y of I minus y of I, which is predicted if you see from the cap, squared. So TensorFlow usage is tf.keras.losses mean squared error. Next one is binary cross-entropy. Measuring the binary classification loss between predicted probabilities and binary labels 0 or 1. Mathematically, binary cross-entropy is represented by minus 1 raised to n summation of I is to 1 to n with yi times log of yi predicted plus I 1 minus y of I into log of 1 minus y of I predicted value. TensorFlow usage is tf.keras.losses.binary cross-entropy. Categorical cross-entropy measures the multi-class classification loss between predicted probabilities and one hot encoded labels. Mathematically, the categorical cross-entropy is represented as minus 1 raised to n from summation of I is 1 to n for summation of j of I to m y of ij log of y of ij predicted value. TensorFlow usage is tf.keras.losses.categorical cross-entropy function. Next one is sparse categorical cross-entropy. Similar to categorical cross-entropy but accepts integer labels instead of one hot encoded labels. Mathematically, the sparse categorical cross-entropy is represented as minus 1 upon n summation of I equal to 1 to n log of y of I, which is predictive value in the bracket of into the index of y of I. TensorFlow usage is tf.keras.losses.sparse underscore categorical cross-entropy. Optimizers. Optimizers are algorithms used to minimize the loss function by updating the model's parameters, weights and biases during training. They adjust the parameters in the direction that reduces the loss, thereby improving the model's performance. Common optimizers are Stochastic Gradient Descent, which is SGD, updates the parameters based on the gradient of the loss function with respect to each parameter. It is basic optimization algorithm used in neural network training. TensorFlow usage is tf.keras.optimizers.sgd, learning rate equal to 0.01. Next is ADAM, which you probably heard about before. This is the adaptive moment estimation. That's what ADAM stands for. Combines the advantages of both AdaGrad and RMSProp algorithms. It adapts the learning rate for each parameter and uses momentum to accelerate training. TensorFlow usage is tf.keras.optimizers.adam and learning rate equal to 0.001. RMSProp, which we saw above. Root mean square propagation. That's what RMSProp stands for. That adjusts the learning rate for each parameter based on the magnitude of recent gradients. It prevents the learning rate from decreasing too fast for frequently occurring parameters. How do you use it in TensorFlow? tf.keras.optimizers RMSProp learning rate of 0.001. AdaGrad, adaptive gradient algorithm. That's AdaGrad. Adapts the learning rate for each parameter based on the historical gradients of that parameter. It allocates more learning to less frequently occurring parameters. TensorFlow usage is tf.keras.optimizers.adagrade learning rate of 0.01. Now, custom loss function and optimizers. You can also define custom loss functions and optimizers tailored to specific tasks or requirements by subclassing the appropriate TensorFlow classes and implementing the desired functionality. Here is an example of you can create a class of custom loss by passing tf.garage.losses.loss. You define initialize a self by saying super custom loss self. These are the constructors, and then call function where you pass the self y true y pred and return loss value. Custom loss equal to custom loss function. Custom optimizer equal to tf.garage.optimizers Adam learning rate of 0.001. Loss functions quantify the discrepancy between predicted and actual values, guiding the optimization process during training. Optimizers adjust the model's parameters to minimize the loss, improving the model's performance over time. By understanding different loss functions and optimizers and selecting the appropriate ones for your task, you can effectively train neural networks and achieve optimal results. Experiment with different combinations of loss functions and optimizers to find the best configuration for your specific problem.